recording. All right, so we're gonna come back to 2.2. Don't think we're just skipping it indefinitely, but we are moving on to 2.4, which is two very important rules. So far, we have the power rule, and we also have the sine and cosine rule. Right? You can get this on Canvas or on Corpusrole, either way. The first rule we're going to learn is the product rule. But before that, just a reminder, like we did last time with a couple of bullet points. We have two functions now that we're going to be dealing with. The first function is just f of x, and that's your y value generating quote-unquote machine, right? If you think of the function as a machine. Given an x, plug it in, get the y value. It tells you where the function is at any given moment, right? F prime, though, is your slope generating machine. It tells you how fast that y value is increasing or decreasing at that moment. Okay, so two functions: y value, slope value. The first rule I'm going to show you is the incorrect product rule, because even as we get further down and into the year, we learn more rules. The product rule seems to be the one that students tend to mess up because they do it like this. This does not work. If you have the derivative of two functions, f times g, it is not as simple as f prime times g prime. The derivative of the product is not the product of the derivatives. If they were added or subtracted to each other, then yeah, term down the line. But you can't do it, okay? But the good news is there is a correct way to do it. You just have to remember what it is. So the derivative of f times g is the following: f prime g plus f g prime. The derivative of f times g is, ready for it? F prime g plus f g prime. 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 Yeah, so you can think about it that way, or you can think about it as just like, hey, we have two factors. We're going to generate two terms, okay? Two factors will generate two terms. And in each term, we take the derivative of just one of them, one at a time. So in the first term, I like to take the derivative of the first one first, because he is standing in front. So the derivative of f goes first, times just g. G just goes along for the ride for moral support. Plus, now f is going along for moral support, times, now it's g's turn. You go, g. Thank you, right? Be kind to each other. Let's give each other the spotlight. F prime first, times g's just standing there, plus now f goes g prime, right? F prime g plus f g prime. Now the cool thing about it is if it works like that for two factors, it works the same way for multiple factors. So if you had like f of x times g of x times h of x with three factors, guess what it's going to be? It's going to be, I'm not going to put the of x, it's going to be f prime, you go first. Or f, you go first. Okay, f prime. And then g and h go along for the ride. Plus, who's next in line to go? G's turn. So f stands fast and it's g's turn, and h stands fast. So now they're on either side supporting him. And now whose turn in the end? H goes last. He doesn't mind. It's f times g times h prime. So that's the whole idea of the product rule. You'll always generate as many terms as you have factors, okay? Three factors generates three terms, two factors generates two terms. And you take the derivative of only one of them in each term, one at a time. It's really hard to mess up the product rule, okay, if you have that idea in mind of taking turns. Really, the only way to mess it up is if you get anxious, right? Take them both at the same time. Right? That doesn't work. One at a time. And the reason it's hard to mess up is because you're always adding them together, and addition is commutative, and you're multiplying them, and multiplication is commutative. So really, you could do them in any order you want. Just make sure that each factor gets the derivative taken of it, and it gets its own term. It shines in that term, okay? So f prime g plus f g prime, 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 f prime g plus f g prime. If that helps you too, that's good. All right, let's try it out. Example one, find the derivative of g of x equals x times that using the product rule, and then verify using the power rule. Okay, So you walk up to this function, like, what's up, function? G is x, that's a variable, times the quantity 5x minus 3x squared. Did you hear me say times? That's a product, right? So I know this is not the way most of us would probably end up doing this problem, but we're going to do it this way so we can verify. We're going to do it two different ways. We should get the same answer, right? So if we walk up to the problem, I notice it's a product of two variable functions. I put the first one in parentheses just to make it stand out. All right, so here we go. G prime of x is, the first factor goes first. What's the derivative of x? It's 1 times the second one goes along for the ride. Plus, now the first one goes along for the ride, times the derivative of the second factor, which by the power rule is 5 minus 6x. Okay, two factors, generated two terms. I took the derivative of the first one first and the second one second. Now let's simplify. If I distribute the 1, I get 5x minus 3x squared. If I distribute the x, I get plus 5x minus 6x squared. If I combine like terms, 5 plus 5 is 10x, and then I get minus 9x squared. So that's the derivative. That function there will tell you how fast g is changing in any given moment. Now, if I didn't tell you about the product rule, or if I just let you take the derivative of this using your own rule, would you do it that way? Probably. You certainly could, right? One of the things I'll say repeatedly this year is simplify early and often. So if you have something like that, it's almost easier, especially if you know you want your final answer to be expanded and collected. It's almost easier to distribute first, isn't it? Yeah, let's see what that would look like. If I distribute the x first before I take the derivative, it's 5x squared minus 3x cubed. Now let's take the derivative. G prime of x. Now I'm just using the power rule, aren't I? Multiply, you get 10x. Subtract, you get 1. Multiply, subtract. Oh, look, did we get the same answer? We did. So that's why I do this one first. Product rule is probably not the way that I would do it, but we did it that way and we did it the other way and we got the same answer. That's pretty cool. That means that our method works, at least for this function. And if you do the correct product rule, it'll work every time. Two factors, two terms, one at a time. F prime g plus fg prime. All right, go ahead and do example 2 on your own. Ready, set, go. Feel free to use your best friends, parentheses. You did them both at the same time. Don't do that. That's the wrong way. One at a time. One, two factors generates two terms. There you go. All right, if you're done, I have it up here. You have two. I put them both in parentheses. So when you kind of say it in your head, derivative with respect to x of 5x cubed times cosine of x, because it's two variable functions, you're going to use the product rule. And again, you always want to take inventory. We'll do this with chain rule later on too. If you have two factors, you should end up with two terms. Two factors should always end up with two terms. All right, so I grouped 5x cubed together. I'm going to call it the first factor. He goes first. He's in front. The derivative of 5x cubed, 15x squared. Times, do we take the derivative of cosine right now? Right now? No. Cosine just goes for the ride. right? Plus, now the first one, 5x squared, gets rewritten, times parentheses, the derivative cosine is negative sign. So again, notice the parentheses I have here. I have it around each of the factors. It helps me keep track of things. This times this times this. And then you can simplify in the end. In the end, you can drop the parentheses and get 15x squared cosine of x, and you can pull the negative 1 from the sign in front and call it minus 5x cubed sine of x. And then from there, if we wanted, we could even factor out like a 5x squared. Later on, we're going to want to use the derivatives, remember. We're going to be setting it equal to 0 quite a bit because we're interested in where those horizontal tangents are. And when something's set equal to 0, it's a lot easier to solve when it's factored. Yeah, let's go ahead and factor it, just for kicks and what's the GCF, the greatest common factor? 15x squared? 5x squared. 5x squared. Yeah. And we factor it out, and we're left with the 3 cosine of x minus x sine of x. So at least we know that this function, whatever it is, does it have any horizontal tangents? What would that do? If I wanted to figure out where this function had horizontal tangents, what could I do? 0 is the slope of a horizontal line, right? So instead of plugging in an x and hoping to get 0, I can just set it equal to 0 and solve. Now, once it's equal to 0, because it's factored, either 5x squared equal to 0 or this parentheses thing is 0. I know right away that at x equals 0, there's a horizontal tangent. Okay. There might be another root from that second factor, but it's not going to be real easy to find. Okay. But at least I know one of them. I know it's 0 because 5 0 squared is 0. I know there's a horizontal tangent at 0. Okay, so product rule is pretty important. Okay, don't mess it up. Don't mess it up. Go ahead and try this one. Take the derivative and then simplify. Put parentheses around things if you need to. 2 factors, 2 terms. 2 factors generates 2 terms. All right, so I went ahead and put parentheses around all kinds of things. 2 cosine of x, I set a variable, times cosine of x. That's how we read that. So it kind of helps you. And the cosine of x is another variable function. So you can associate the constants, the constant multiples like 2, with the closest variable function. So you don't have to like say it's 2 parentheses x parentheses cosine. You can call it 2x. So with those 2 variable factors, I'm going to have 2 variable terms. So here we go. The derivative of 2x is 2 times cosine goes along for the ride, plus 2x goes for the ride, times the derivative of cosine is negative sine. So that's a good way to kind of take inventory. 2 factors generates 2 terms. Now, look at this last one here. It's minus 2 sine of x. Do I need to use the product rule there? I put 2 in parentheses. Do I need to use the product rule there? No, I don't. Because 2 constant multiples go along for the ride. So it would be minus 2 times, what's the derivative of sine? Cosine of x, right? So that's how you could do it. Now, could you, instead of thinking of it as like that, that's how I thought of it, right? 2 sine of x, 2 goes for the ride, cosine of x becomes, or sine becomes cosine. Could you say that 2 is its own factor and use the product rule? It should work, right? Now, this is a good opportunity to kind of warn you about, being careful with negatives. What's important about the product rule is it generates 2 terms, right? So if you're doing the product rule behind a negative sign, you got to be careful because it would need to distribute to those 2 terms. So there's a couple ways to do this. You could put brackets behind the negative and now use the product rule. So let's say 2 is its own function. 2 factors, 2 terms. What's the derivative of 2? 0, right? Times sine goes along for the ride. Plus 2 goes along for the ride times the derivative of sine, which is cosine. Now, of course, what happens to the first term? With its 0 there, it goes to 0, and we're just left with minus 2 cosine of x, okay? But had that been like a 2x sine of x, that negative would need to be distributed there. So there's proof that you don't need to elevate constants that are multiplied. You don't need to elevate them to their own status of function. Just associate them with the closest variable function. So now if we clean up, it's 2 cosine of x minus 2x sine of x. We'll pull that negative in front. And then, of course, we get minus, nothing to distribute. It's just 2 cosine of x. Do you notice anything there? Do we have any like terms? Yeah, your 2 cosine of x's are there, and they're opposite signs, so they actually cancel, and you're left with minus 2x sine of x. And again, notice I'm working straight down with no equal signs, because we start with an expression, and as soon as we take the derivative, we get rid of it. So that one simplified down pretty nicely to a single term fella. All right, I was going to do the same thing with 10x squared. I was going to call 10 its own function and use the product rule. We don't need to do that anymore because I talked about it up here. There's no need to call a constant multiple its own function. It's just extra work. And be careful behind a negative. Product rule generates 2 terms. All right, we're in here till 35 after, right? So we have like 10 minutes. I forgot my watch today, and I keep looking at my wrist saying, oh, that's what my wrist looks like under my watch. I miss it. I guess there's other ways to tell time, right? Like a sundial on your wrist, or look at the sun in the sky. You can tell how high it is in the sky. What about a rain gauge on your wrist? Oh, a few of you know that is one way to keep time. We're going to get to that later on. Okay. The quotient rule is I got 2 pieces of bad news over lunch break, and I'm trying to stay happy and positive because the quotient rule needs to be taught with a really positive, happy mindset. So with 10 minutes left, I don't want to waste it, but I'm going to be manufacturing happiness, okay? but I can do it. I can do it. Let's do the incorrect quotient rule. The incorrect quotient rule, much like the incorrect product rule, is oversimplifying things. You'll know it's wrong because it feels wrong. If you have the derivative of a quotient of two variable functions, f divided by g, it's not the quotient of the derivatives. You can't just take the derivative of the top, divide it by the derivative of the bottom. It doesn't work. Even if you know the bottom can't be 0, that doesn't work. Okay? The good news is there is a way. And here's the correct way. The derivative of f divided by g is gf prime minus fg prime all over g squared. Oh, yeah, oh, yeah. Gf prime minus fg prime over g squared. Oh, yeah, oh, yeah. I don't know. That doesn't sound as good as like f prime g plus fg prime. F prime g plus fg prime. Let me try it again. Gf prime minus fg prime all over g squared. Oh, yeah, oh, yeah. I think we could do better than that. I think we could do better than that. Okay. But notice it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. So like the product rule with two factors, one on the top and one on the bottom, we're generating two terms, yes? But it's subtraction in between there. Is subtraction commutative? Heck no. So unlike the product rule that's hard to mess up as long as you're in the spirit of two terms, this one you can easily mess up if you take the derivative of the wrong one first. You do need to take the derivative of the numerator first. And that might be obvious, right? Because when you walk up to a fraction, usually the numerator is the first one you come in contact with. So derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. I'm not even going to try and make that into a little jingle. But there's another way to do it. Watch, okay? Just bear with me here. If you let, if we take the derivative with respect to x, if we let the top function be the high function, and we let the bottom function be the low function, would you be okay with that? High is in the top, low is in the bottom. That makes sense, right? High over low. Then this rule becomes low times the derivative of the high. I'm just going to call that d high. Is that okay? Minus the high function times the derivative of the low function all over the low function squared. So this becomes a little bit more melodic. Low d high minus high d low over low low. Right? That sounds better. Low d high minus high d low over low low, or low squared. Well, here's what the great Mr. Peck did. Mr. Peck, he likes alliteration, and he likes Snow White and the Seven Dwarfs. And he also likes Wilson, a character from a show. Yeah, Wilson. He always came over the fence and said, "Hey, Heidi ho, neighbor." So he turned the low function into the ho function, which is easy to remember. Low rhymes with ho, so it's easy to remember. High function is in the top, and then the ho function is on the bottom. This then becomes ho d high minus high d ho all over ho ho, or ho squared. That is easy to memorize. Yes, sir. Ho d high minus high d ho over ho ho, right? Ho d high minus high d ho over ho ho. Ho d high minus high d ho over ho ho. Ho d high minus high d ho over ho ho. Now, you can screw it up if you go high d ho minus ho d high over high high. Right? How do you know, here's what he also said. He said it's easy to remember ho d high minus high d ho over ho ho. But if you need extra help, start with the ho and end with the ho, right? You start with the ho and you end with the ho, right? Can you get an amen? Start with the ho and end with the ho. Oh, and by the way, you also got two hoes in the bottom. You got two hoes in the bottom. Yeah, you got hoes everywhere. Hoes all over the place. Look at that. Hoes on the outside. Start with a hoe, you end with the hoe, and you got two hoes in the bottom. Now you're not going to mess it up. Ho d high minus high d ho over ho ho. Ho d high minus high d ho over ho ho. Ho d high minus high d ho over ho ho. In fact, I don't even call it the quotient rule. I call it the ho d high rule, not the ho rule. I call it the Hody High rule. The Hody High rule. Start with a ho, you end with the ho, and you got two ho's in the bottom. Ho ho. Okay? Hody High minus Howdy Ho over ho ho. Hody High minus Howdy Ho over ho ho. And of course, we all know ho can't be zero, right? You can't divide by zero. Can't have zero hoes, right? So I put these images here because these are like Mr. Peck likes these, like the seven dwarfs, right? When they go to work, or if you've ever ridden Mine Train at the Magic Kingdom, they hi ho, it's off to work we go, right? Hi ho, hi ho. Now hi ho starts with the hi, right? They don't say ho hi, it's off to work we fly or something. I don't know. And then here's Wilson. Here's Wilson from the show. He always came over the fence and he would just say, Hody hi, neighbor. Or he'd say, Heidi ho. He'd say, Heidi ho, neighbor, if you ever watched. So that's another Heidi ho. When I greet you at the door from now on, I'm going to say Hody hi. That's going to be my greeting. Instead of Heidi ho, which some people say is a greeting, I'm going to say Hody hi. That's going to be our greeting, right? Like bust out the calculus, BOTC. Our greeting is going to be Hody hi. Hody hi, how's it going? Hody hi. And why would we want to say Hody hi? To remind you to start with a what? Ho. Hody hi minus Heidi ho over ho ho. Now, look at this. I put this image here. This is a little obscure. This is because of the denominator, right? If Santa Claus is in a hurry, right? He's trying to get fit for Christmas, but he's in a hurry. He doesn't have time. Santa Claus normally says what? Ho, 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 3 times. But Santa Claus in a hurry only says ho, ho. Gotta go, you know. I don't have time for that third ho. Whatever. I don't know. It's just ho, ho. If he's in a hurry, he only says ho, ho, right? You could draw that ho, ho, right? Ho, ho. Gotta go. Don't have time for the third ho, you know. But have fun with your hoes, right? Ho, ho. Hody hi minus Heidi ho over ho, ho. And then it's F prime G plus F G prime. F prime G plus F G prime. F prime G plus F G prime. Hody hi minus Heidi ho over ho, ho. Hody hi minus Heidi ho over ho, ho. Hey, Hody hi minus Heidi ho over ho, ho. Hody hi minus Heidi ho over ho, ho. There you go. I hope you remember that.